Well, let me say good night to everyone. I'm saying good night because we have a speaker from Japan today. It's 11 p.m. Good morning, good afternoon, good evening. So today is our pleasure in the CRM camp seminar to have Kaname Matsue from Kyushu University. So Kaname obtained his PhD in 2011 from Kyoto University under the supervision of Professor Hiroshi Kokubu. And from 2011 to 2013, he was an assistant professor at the Tohoku University, where he worked at the intersection of discrete geometric analysis and material science. And then he was an assistant professor at the Institute of Statistical Mathematics in Tokyo, where he stayed there until 2016. And since then, he's an assistant professor at Kyushu University. In 2015, he was awarded the Prize for Excellent Young Applied Mathematicians from the Mathematical Society of Japan for his work on rigorous numerics of homoclinic orbits for fast-flow systems. His mathematical interests consist of dynamical systems, ODEs, rigorous numerics, fast-flow systems, combustion science, engineering towards sustainable energy generation, and finally, finite time singularities, blow-up situation, a topic which he will talk about today. So please, Kaname, the floor is all yours, and tell us about rigorous numerics of blow-up solutions.
Yes, thank you for nice introduction, Jeff-Philippe. I'm very honored to be invited to this great seminar series. Hello, everyone. I'm Kaname Matsue from Kyushu University, Japan. Today, I'll talk about rigorous numerics of blow-up solutions with several fundamental treatments of blow-up solutions from the viewpoint of dynamical systems. Oops. All right. So the blow-up behavior can be typically seen in nonlinear ODEs and PDEs, which is characterized by the divergence of the norm of solutions at a finite time. This blow-up behavior can be seen in many ODEs and PDEs, as I mentioned, such as nonlinear heat equation or nonlinear Schrödinger or Keller-Ziegler systems. And there are so many numerical studies for detecting blow-up behavior. But there are several non-trivial issues to characterize blow-up behaviors so far. First of all, typical treatment of blow-up behavior assumes large initial data, namely the norm of initial data is sufficiently large for detecting blow-up behavior. So and the second one is asymptotic behavior of blow-up solutions. In some cases, the asymptotic behavior is a priori given, namely given ansatz of blow-up behavior is assumed. I'm not sure if it is where the origin of such ansatz and assumption is, and my current study is the systematic treatment and the construction of systematic methodology for detecting blow-up behaviors by means of dynamics and infinity, and possibly with rigorous numerics of these types of solutions. But there's another difficulty for detecting blow-up solutions by numerics, which is the treatment of infinity. So the infinity cannot be expressed on computers without appropriate treatments. So the treatment of infinity is also an essential issue for studying blow-up behavior. To overcome these difficulties, I have constructed several methodologies for detecting blow-up behavior from the viewpoint of dynamical systems. So let me first introduce this machinery. Then I will introduce the rigorous numerics of blow-up solutions, and finally I'll show several primitive examples. Okay, so in our arguments, the vector field generating the dynamical systems is restricted to a certain class called case homogeneous classes. And first of all, let me introduce the case homogeneous function, which requires scale invariance of polynomials like that, but the scaling exponents can be different among different exponents, and the correction of these exponents is called the type in this talk, and the degree of the scale invariance k appeared here as the order of the case homogeneous functions, and the vector varied function counterpart for case homogeneity is also introduced here, but to characterize the case homogeneity for vector varied functions, this scale invariance is uniquely determined by the type and the order as a common factor. For example, look at this vector varied functions. Obviously, this vector varied functions is not homogeneous in the sense of polynomials. But when introduce R scaling for the first variable u and R square scaling for the second variable v, then we have this the scale invariance for both components of vector varied functions shown here. But the key point is the rule over this scale invariance. As for the first component, the order is of this scale invariance is given by the first component of type under common factor 1. While the second scale invariance is determined by the second component of type and a common factor 1. Second factor given by 2. Okay, yeah, and the common factor 1. So consequently, we can say that this vector field or vector varied function is case homogeneous of type 1, 2, and order 1 plus 1 equal to 2. This is a case homogeneous functions or case homogeneous vector fields. But this is too restrictive to consider the dynamical systems. So we generalize the class of our vector varied functions, which is asymptotic case homogeneity at infinity. So our current interest is blow-up solutions. So the case homogeneity is sufficient to be satisfied around infinity. So that's why we introduce asymptotic case homogeneity consisting of the case homogeneous part and the remaining part. The remaining part here means the lower order parts compared with the case homogeneous part, characterized by the decay estimates. So looking at this example, a remaining term minus u is added in the second component compared with the previous example. So we can so this vector field is not even case homogeneous, but we can choose the vector fields shown appeared in the first example as a case homogeneous component. Then we can show that the additional part it's very small at infinity compared with the case homogeneous part. So we can say that this vector field is not case homogeneous, but asymptotically case homogeneous of type 1, 2, and order 2. So this class of vector fields are central issues in our consideration. Yes. Okay. So next, we go to the treatment of infinity. So the basic idea to treat infinity is application of compactification. So this is a essential idea of compactifications. At first, prepare phase space Rm and the hemisphere with radius 1 and the same dimension as the original phase space. And we assume that these two manifolds are attached at the north pole of the hemisphere and the origin of the original phase space. Namely, these two manifolds are tangent at the corresponding points. Then we correspond the given point on the original phase space to an intersection point of the line segment connecting the given point on the phase space and the center of the hemisphere. And then we obtain the unique intersection point and project this point onto the original phase space. This operation is explicitly given by this relationship used by means of the Euclidean norm of the original phase space. And using this correspondence, we can characterize the infinity by means of the point on the hemisphere. For example, looking at the given point on the original phase space and move this point to the infinity at a certain direction, then the corresponding intersection point on the hemisphere goes to the boundary of the hemisphere with the same direction as the direction of divergence of the original given point on the phase space. So the infinity in the original phase space corresponds to the boundary of the hemisphere. So this is a fundamental idea of the compactification and the treatment of infinity within a bounded object. And this treatment can be applied for homogeneous problems or asymptotically homogeneous problems. So I have introduced a quasi-homogeneous counterpart of this idea, which is defined as a quasi-Poincare compactification of a given type. The type here means the corresponding notion introduced in the asymptotically quasi-homogeneous vector field. Okay, so for detailed definition of this quasi-Poincare type quasi-Poincare compactification, we replace the Euclidean norm here by appropriate functional determined by some exponents given by the given type alpha here. Then replacing the points on where the Euclidean norm is used for determining the compactification by P by function P. We define the mapping of the original phase space to the quasi-hemisphere in the similar way to Poincare type compactifications. And we can also consider the localized compactifications, which is well applied to dynamics at infinity by several.
That's a question. What
yes?
does it mean when you require alpha 1 times beta 1 equal to alpha 2 beta 2 equal to c, which is in positive integer in the setup?
Yes. Yes, thank you for your question. So the exponents alpha are given a priori. Then beta is defined later. So that the product of alpha and beta with the same index, namely index 1, index 2, index 3, is identical to attain some integer. For example, if alpha 1 and alpha 2 is given as 1, 2, then we choose beta 1 and beta 2 as 2, 1, for example. Yeah. And so, then the product is identically to fetch the integer.
Yeah, but I'm not sure why you want to C to be an integer, because you want to define low y. Then as long as C is bigger than 1/2, you can define a distant function, right? So why you require C to be a positive integer? Does that any relationship with some kind of blowing up rate, or I'm just curious.
Yes. I think this relationship can be generalized in some appropriate way, but for a while, for simplicity, just for simplicity, we assume that the product is identical integer here.
Okay. Okay. Thank you. Thank you. Thank you.
Yeah. Thank you for your question. Yeah. So going back to the compactification. Yeah. We can consider the directional compactification of the given type alpha, and which is geometrically given by the tangent space of the Keisai hemisphere given in the Keisai Poincare compactification at the point on the boundary, like this. And in both cases, the boundary of the hemisphere or the upper half tangent space can correspond to the infinity, and we shall call these boundaries the horizon, the corresponding object of the infinity. Then we can also consider the third type of compactifications, the so-called parabolic type compactifications, which corresponds the original point, the points on the original phase, phase space to a point on the parabola, and project it onto the original phase space, and the actual expression is given implicitly, but the geometric correspondence is given in these figures, and we can also consider the Keisai homogeneous counterparts of these kinds of compactifications. Yeah, given here. In this case, the infinity in the original phase space also corresponds to the boundary of parabola type objects, and we shall also call this boundary the horizon, corresponding to the infinity. Okay, so now we have three types of compactifications, and depending on the situations, we can choose appropriate compactifications. For example, the Poincare type compactifications gives us a geometrically simple interpretation of the treatment of infinity, and this compactification is defined globally in the original phase space. But this the definition of Poincare type compactifications includes square root or fractional power. So this provides an artificial difficulty for treating dynamics at the infinity. Just as for the sorry, but we skip the details of directional compactifications because we don't treat this compactification in detail here. So as for the parabolic type compactifications, so the definition of this parabolic type compactifications does not include square roots or fractional powers. So we can overcome the artificial difficulty for treating dynamics at infinity. And in particular, the linear stability analysis still makes sense. We shall mention later. But the actual implementation is so complicating, so we need lengthy calculations for treating dynamics at infinity by using parabolic type compactifications. But once we obtain a corresponding objects, then we can consider dynamics at the infinity without any artificial worries.
Can you say
Okay.
what is sign change structure in the direction?
Yes, yes. So this is a information of solution profiles attaining positive value or negative value or positive value, negative value during the time of evolution of solutions.
Also, it's right, like we have to calculate a sphere in R3, but we can we cannot use a uniform coordination. We have to like separate like positive part and negative part and do something.
Yeah.
Okay, thank you.
Yeah. So we require multiple directional transformations if we treat the sign changing structures when we apply directional compactifications, and Fitch provides extra difficulty for numerical treatments. Indeed, yeah. All right, thank you for your question. Yeah. Okay, so now we go to the main part for the theoretical treatment of blow-up solutions. Now we consider the initial value problem of autonomous ODEs, but we assume that the vector field F is smooth, asymptotically quasi-homogeneous vector field of, and the type and the order is given a priori. Then we apply the same type of compactifications. Then we consider the dynamics at infinity later. But note that in the present case, the blow-up solution for the initial value problems is the divergence of the functional p introduced in the Poincare type compactifications are shown here at a finite time. This is our definition of blow-up solutions for the given ODE here. Okay, so now once we determine the type of the vector field F, we can introduce the corresponding type of compactifications. Here we shall apply Poincare type compactifications. Then we transform the original vector field to the following. So this is this looks so complicating, but this is just a transformation of the original vector field under the compactifications. But this is just the transformation of vector fields. So the singularity at infinity is still inherited in this vector field. Namely, this vector field is still singular on the horizon, which is characterized by the level set of the function of p. Then we cannot treat the dynamics at infinity in present setting. But fortunately, we obtained the following lemma. This vector field is singular on the horizon, but the order of divergence is uniquely determined by the order of the original vector field. Namely, this vector field is order of kappa to the k, as kappa going to the infinity. And this characterization of order is independent of the components. Although the actual form of vector fields looks complicating. This shows that the order of divergence of this vector field is uniform. So we can introduce a uniform time scale transformation introduced by this guy, kappa to the k, to obtain the desingularized vector field like this. So this vector field is formally obtained by dividing the transformed vector field by the kappa to the k, which looks so simple, but the resulting vector field here, called desingularized vector field, is continuous, including the infinity. Sorry, in this case, including the horizon. So the dynamics at infinity makes sense in terms of the dynamics of this desingularized vector field on the horizon. This is a central idea for the treatment of dynamics at the infinity. And this time scale
desingularization. Sorry.
Yes.
Recall what is kappa again in the
kappa? Yes. Kappa is given by where is the definition of kappa? Yes, this guy.
Oh, just some. Okay. Just some kind of distance, right? Yeah.
Yes, exactly. Yes. So and this formulation is specific to the Poincare type compactifications, but this this scenario can be applied to other type of compactifications like this. So we can systematically choose the timescale desingularizations to obtain a desingularized vector fields, including the horizon. Namely, for any compactifications introduced here, we can treat the dynamics at the infinity through these compactifications and timescale desingularizations mentioned here. Yes. So anyway, we can characterize the divergent solutions in this machinery. Namely, we obtain this proposition. So going back to the original ODEs, we consider the monotonously divergent solutions of the original ODE, and namely the divergence at a certain direction, which shall be called X star. Then we obtain one-to-one correspondence to this such a divergent solution to a global trajectory, a time global trajectory of desingularized vector fields asymptotic to the point X star on the horizon. So in other words, the divergent solutions over the original vector field can be characterized by the global trajectory on the stable manifold over a point on the horizon. And indeed, we can also prove that the point X star characterized by this divergent solution is actually an equilibrium of the desingularized vector field. So the stable manifold mentioned here is associated with the equilibrium on the horizon. So once we obtain this correspondence, we can apply the standard machineries in dynamical systems to characterize divergent solutions. But this is still the characterization of divergent solutions, not blow-up solutions yet. So what's the characterization of blow-up solutions? this is a finiteness of the maximal existence time characterized by this formula introduced by timescale desingularization here. But fortunately, we obtain the following criterion for characterizing blowup. Okay, and now we assume that the desingularized vector field is not only continuous but also C1, including the horizon. This is essential for Poincare type compactifications, but in the case of directional or parabolic type compactifications, this assumption is automatically satisfied, so it is not essential. But the essential part is the next one. A point on the horizon, it's a hyperbolic equilibrium of the desingularized vector field. Then we can show that the solution of the original ODE, whose image is located on the stable manifold of this hyperbolic equilibrium on the horizon, is actually a blowup solution. So the hyperbolicity of equilibrium on the horizon is an essential assumption in this treatment. Moreover, we obtain the asymptotic behavior of such blowup solutions, which is uniquely determined by the type and the order of the given given vector fields. So, this, analytically, this is very essential because in typical arguments of typical analytic arguments of PD, blowup solutions in PDs or ODEs, this asymptotic form is assumed a priori. But in the present case, this formula is obtained by the first assumption of the original vector field. This is very essential. Okay, so
a silly question. So when you actually study the case when like the flow on a compactification, so what you do is like I have a particle, I follow the vector field, then it somehow collide into the boundary, so it's rather not getting tangential to the boundary. Is that right the case for the first type 1 blowing up, or it's right the particle move to the boundary, but as it approaches boundary, it becomes more tangential?
Sorry, I mean, I missed your point.
Oh, okay. Maybe let me do something. So what you have is like you have a ball. So ball is like you change your equation, right? So in your graph is like you have a point, then follow the vector field, it just jump into the boundary. But normally, if we have a C1 field, it should be like somewhat like this. It will become more or less tangential to the boundary, right? Not exactly hit at the boundary, right?
Yeah, I guess the question is it possible that the solution arrives like tangentially to the boundary?
Yeah. Well, from your things, right? Like you have a point, and then you just jump into the boundary. Like there's like sometimes
from this figure.
Yeah. Like just jumping.
Yes. It is also the case to the convergence more tangentially like your figure. Yeah.
Oh, okay. So the things like when the become approach boundaries become more tangential to the actual.
Yeah.
Okay.
Yeah, but it is not essential for characterizing blowup solutions. Yeah.
Because I think blowup solution can be very singular because then you cannot discuss any flow around the boundary, right?
Yeah. All right. Okay. Thank you so much. Okay. So let me summarize our treatments. For given autonomous ODE, determine the type and order of the asymptotic case homogeneous vector field first. Then we apply the same type of compactification and introduce the time scale desingularization given by the order of the vector field F. Then we obtain the desingularized vector field. In this setting, the dynamics at infinity makes sense. Then we find an equilibrium on the horizon and if necessary, verify the hyperbolicity of this equilibrium, and validate the trajectory on the local stable manifold for the desingularized vector field. And then we can characterize the blow-up solutions for the original problem. Then, if necessary, we have to compute the rigorous bounds of Tmax, but it is a part of rigorous numerics. But part 3 and 4 are can be realized in a standard way of rigorous numerics for dynamical systems. So part 3 and part 4 isn't so difficult once we can introduce a desingularized vector field. So the non-trivial part will be the final part, namely the computation of rigorous value of Tmax. But notice that if we want to know that Tmax is finite, the hyperbolicity of the equilibrium on the horizon is sufficient. But if we know the actual value, we have to go to the next step, which is the rigorous numerics of blow-up profiles. Yes, the most difficult part in rigorous numerics for blow-up solutions would be the computation of this integral. There are two difficulties for characterizing this integral. One is the integral over infinite range integrals over the desingularized time scale. And the second part is this integral should be done along the solution trajectories, in particular blow-up profiles. So there are two difficulties, but how do we overcome these difficulties? This is a central question for detecting the actual value of Tmax. So to overcome these difficulties, we first divide the integral into those over finite range and infinite range. As for the integral over finite range, we directly integrate the ODE and compute this integral directly using the interval arithmetic or some other numerical tools. But the essential point would be the second part. So we apply the asymptotic behavior of the solution trajectories on the local stable manifolds to estimate this integral. This is an essential part for detecting the actual value of Tmax. Then we have two tools. One is local Lyapunov functions, and the second one is a parameterization of local stable manifolds. But due to the time limitation, I briefly introduce the essential idea. Okay, the application of local Lyapunov function is a construction of locally defined Lyapunov functions given by the quadratic form locally defined around an equilibrium. So the actual construction of Lyapunov function is sufficient to verify negative definiteness of associated matrix, which also appeared in the verification of cone conditions in topological arguments. But anyway, during the verification of this negative definiteness, we can systematically construct locally defined Lyapunov functions around the equilibrium. Then once we obtain such a Lyapunov function, we can estimate the upper bound of the maximal existence time as follows. First, we detect equilibrium on the horizon. Then we construct a local Lyapunov function around the equilibrium. Then, thanks to the property of Lyapunov functions, we obtain this inequality from the property of Lyapunov functions. Moreover, if the equilibrium on the horizon is asymptotically stable, we can also prove that the actual value of the Lyapunov function is strictly positive of the equilibrium. Then along a given solution orbit, we have a one-to-one correspondence between the times the parameterization by time variable tau and the parameterization by the value of Lyapunov function L. So our main idea here is to transform the integral over tau to that over capital L, namely the value of Lyapunov functions. And then we can transform the infinite time integral to the finite range integral, which can be validated by hands and by interval arithmetic. As an example, here I show a very brief estimation of Tmax. For example, assume that there is an stable equilibrium on the horizon, and the local Lyapunov function is detected around here. Then we compute the trajectory for a given point and assume that the trajectory goes into the domain of definition of these Lyapunov functions. Then we obtain the lower bound of Tmax as this integral. Tau here is the time going to this domain. Then once we can verify that the solution trajectory goes into the domain of Lyapunov functions, we can estimate the upper bound of Lyapunov, maximal existence time Tmax as follows. So the Tmax minus Tn, given by this integral, is estimated by the Euclidean norm for the case of homogeneous Poincare type compactifications. But this integral can be estimated by the value of Lyapunov functions using these inequalities. Then the integral over tau is transformed into the integral over the value of Lyapunov functions. Then we can exactly compute the integral over Tmax minus Tn, or we can obtain the upper bound of Tmax minus Tn as a value which is computable on interval arithmetic, for example. Then Tn is a lower bound of Tmax, and Tn plus this upper bound is attained as a upper bound of Tmax. So this is our essential idea for evaluating Tmax by means of Lyapunov functions. So this is a case of stable equilibrium on the horizon, and ultimately this idea can be applied to saddle type blow-up solutions, but heuristically we cannot validate the relationship mentioned before by the direct integration of ODEs due to the very high sensitivity of vector fields around the saddle type equilibrium. So we propose the second machinery for detecting blow-up solutions, even available to saddle type equilibria, which is a parameterization method. Okay, so now we consider a polynomial vector field having a hyperbolic equilibrium x tilde here, and we assume that the Jacobian matrix at this hyperbolic equilibrium has distinct eigenvalues, and stable eigenvalues, namely negative eigenvalues here are detected in advance. And we further assume that the non-resonant conditions, which is necessary for the unique solvability of parameterization problems. And the parameterization of the local stable manifold of this equilibrium is given by a map defined on the lower dimensional parameter space to the original space, including information of hyperbolic equilibrium and the transformation matrix consisting of stable eigenvectors, and the commutative relationship among the nonlinear dynamics and linearized dynamics on the parameter space is also required. Roughly speaking, the linear stable dynamics on the parameter space express all necessary information on the nonlinear dynamics on the stable manifold. And this linear dynamics is called model dynamics. So all problems of our interest is reduced to the model dynamics once we obtain the parameterization. So our problem here is to compute the parameterization. But there is a general argument for computing parameterization, which is given as follows. So the commutative relationship among nonlinear dynamics and linear stable dynamics on the parameter space is equivalent to the solvability of the partial differential equation called the invariance equation, determined by the stable eigenvalues and the original vector field here. So the calculation of parameterization is reduced to the solvability of these partial differential equations. But now we further assume the ansatz of parameterization, namely the convergent power series. Using this ansatz, the invariance equation is further reduced to a zero finding problem of infinite number of algebraic equations. Now notice that if the vector field F is assumed to be a polynomial vector field, okay? But anyway, the computation of the parameterization is reduced to the zero finding problem of infinite dimensional equations. So we consider this zero finding problem in appropriate to Banach spaces. In the present case, the Banach space is chosen as a product of discrete L1 space, possessing a Banach algebra structure to so that the error band estimate can be easily obtained. Okay. Anyway, if we assume that this zero finding problem has a has a solution on the Banach space, then the solution determines the parameterization of a local stable manifolds. Namely, the parameterization is one-to-one on the parameter space, and this parameterization is a real analytic function on the parameterized disk, and the image of the parameterization. The image of the parameter disk under the parameterization is exactly the local stable manifold of the hyperbolic equilibrium. So this theorem shows that the computation of a local stable manifold of hyperbolic equilibrium is reduced to the to solve this zero finding problem. But this is attained by computer assistance by Newton-Kantorovich type arguments and the radial polynomial approach. But I skipped the detail of these methodologies because many speakers in this seminar already introduced these machineries. But going back to our original problem, the computation of Tmax, this parameterization gives us the very big benefit for characterizing Tmax. But it depends on the choice of problems and the choice of compactifications. So I show the example later. Okay, so it's 10 minutes. Is left, so I go to the final section, namely the examples. Okay, the first example is this this ODE shown in the example of K-sign homogeneous vector fields. So this vector field is K-sign homogeneous of type 1, 2, and order 2. So we apply the K-sign parabolic type compactifications of type 1, 2. Then we obtain the corresponding desingularized vector field, which is polynomials of the 7th order. It looks complicating, but anyway, once we obtain this vector field, we can study the dynamics including the horizon, namely infinity. In particular, we find totally 4 equilibria on the horizon, and one of which is a sinc type. So we can validate the global trajectories asymptotic to this equilibrium using the ODE integration and Lyapunov function validations, for example, which correspond to the blow-up solutions for this problem. Yeah, these are some sample results. So this in this result, we have chosen two sample initial points around here, but focusing on the initial point of -0.1 and -0.0001, the solution, the second component of solution goes to negative ones and going up to the positive value again during the time evolution. So this validation of blow-up solutions capture the sign changing blow-up profiles. But in the case of parabolic type compactifications, we do not worry about the sign changing structure or necessity of multiple local charts. And then we can, in particular, we can directly validate the blow-up solutions with actual blow-up profiles and actual upper bounds and lower bounds of blow-up times like this. So this is the first example, and we go to this the second and the third examples involving the equilibrium, saddle type equilibrium on the horizon. Yes, the second example is the vector field mentioned in the definition of asymptotically Keisai homogeneous vector field. So as I mentioned, this vector field is not Keisai homogeneous, but asymptotically Keisai homogeneous of type 1, 2. Yeah. So we apply Keisai parabolic compactifications of type 1, 2 to detect the global nature of blow-up solutions. Then we obtain this desingularized vector field. So this vector field consists of 13th order polynomials, while the original vector field is at most order 3. So the actual treatment of this vector field is so complicating. This is one of the disadvantages of for the application of parabolic compactifications. But anyway, as in the case of the first example, we obtained 4 equilibria on the horizon. One of which is sink, and 2 of which are saddles, and one of which are source. Then in this example, we focus on the connecting orbits among a saddle equilibrium on the horizon, and the origin being a saddle equilibrium and a bounded source. So we can validate the connecting orbits among these equilibria in a standard way, but this chain of connecting orbits has a special structure, namely this chain of connecting orbits separates initial points to time global trajectories and blow-up solutions. For example, we have validated 4 different types of global trajectories for desingularized vector fields. So zooming up the initial points like this. So in this example, we have chosen 2 initial points close to the origin, and close to the saddle equilibrium on the horizon. But in both cases, one solution goes to the equilibrium on the horizon, while the other solution goes to a bounded sink, namely the interior of the image of compactifications, which provides time global solutions in the original vector field. But such a nature can be seen for no matter how large the initial point is. Namely, even if we choose initial point very close to the saddle equilibrium on the horizon, but a point on the one side of the solutions doesn't blow up, but converges to a bounded data. So this example shows that the blow-up criteria is characterized by complex nature. I mean that the magnitude of initial points is not always essential for detecting blow-up solutions. in the introduction, I mentioned that in typical arguments of blow-up solutions in PDs, the large initial data can be essential for detecting blow-up solutions. But this example shows that such a magnitude of initial points is not essential. Such a structure is given by the saddle type blow-up solutions. Namely the saddle type equilibrium on the horizon. Yes, so 1 minute is left. So I only show the detection of T max in the with the parameterization, and I stop my talk. So going back to the second example, yeah. So we have a saddle equilibrium on the horizon here, namely here. Then parameterization method can provide the local stable manifolds of this equilibrium. Then we have obtained the parameterization of this saddle type equilibrium on the horizon. But in this case, the maximal existence time is given by this formula. So this formula looks complicating, but essentially given by the formula of time scale desingularization and the formula of parameterization. But the essential point here is in the case of Lyapunov functions, we only obtain the upper and lower bounds of Tmax. But in the case of parameterization, we can obtain the exact formula for detecting Tmax as a function of initial points on the local stable manifold. So and this is also the case of multi-dimensional local stable manifolds. So this result provides us more detailed analytic arguments of blow-up nature from the quantitative viewpoints. Yes, so I'm sorry, but the time is already limited. So I stop my talk here, and thank you for your kind attention.
Thank you very much, Kaname.
Yeah, thank you very much.
Are
there any questions or comments?
I have some questions, if you don't mind. So I keep asking so many questions that you don't have time to finish the presentation. Yeah. And also, by the way, it's a very nice talk. I'm very interested. So I think in your first example, you have equivalent at the boundary, right? And you can define some Lyapunov function. So I think the flow is somehow sync like to this one exponentially somehow.
Yes.
And you are designing some flow, they all hit this one, and you are saying for this particular flow, you will hit this region for a finite time. So normally, I think you are doing some numerical things to ensure that happens. But normally, how to select a point that will somehow hit the Lyapunov region in a finite time in general? Or you have some proof? Because maybe I didn't understand your idea fully. You think like you started from one point, you hit as the Lyapunov region in finite time, and then in the Lyapunov region you can easily go into the equivalent, which is exactly the blowing up point, right? So how to ensure a point that travels into the Lyapunov region in finite time?
Yes. We have actually integrated the ODE, and in this case the desingularizer vector bit. Then we validate the value of solution trajectories at a certain time. For example, at a certain value of tau. Then we check the bound of solutions at a certain time, it's completely included in the domain of Lyapunov functions.
Oh,
So,
that's quite interesting.
Yeah.
So is this paper, right?
Yes, exactly.
Okay, okay. Thank you. I'll check this paper later.
Yeah.
Thank you.
Yeah, and the Brab validations for stable involving stable equilibria on the horizon are essentially identical. I just showed here. Yeah.
Okay, okay.
I also have several questions.
Yes.
If I may. So the first one is concerning the choice of this compactification.
Yes.
You did not choose the so to say the usual stereographic projection, where the whole of infinity is mapped to the north pole of the hemisphere.
Yes.
And
yes.
so why is that disadvantage for some reason? So why is it a disadvantage to get the whole of infinity mapped to one point? Then in my stomach feeling, that would facilitate some things when you just have one target point, so to say, for proving a blow up.
Yes. So let me answer this question. Yeah. So actually, we have I have introduced these three kinds of compactifications, but I didn't introduce the one-point compactifications as you mentioned. Yeah. Yes, we can choose such kinds of one-point compactifications, namely the additional point corresponds to the infinity. But in this case, the resulting vector field, namely desingularized vector field, is highly degenerate at the infinity. So even for the linear, even if the original vector field is linear. So we have to introduce additional blowing up or desingularization at the infinity, but the resulting desingularized object is, in my impression, one of them I introduced here. Yeah, and that's why I didn't mention about the one-point compactification here.
So this singularity, which is then created by this one-point compactification, is so terrible that you cannot treat it at all. Or so I see that the advantage of that is that you don't have to search for the point x star, so to say. You know that it's this point if you are able to prove blow up. So it's too terrible to. Okay, I understand. Yes.
I guess it's because the blowing up is non-radial. So if you choose different direction, then you will certainly have different kind of behavior. If you just treat the one point at a one point, then you should generally think all the directions should be identical.
It's clear that this is terribly singular, but it's not so clear if that can be desingularized or not. But okay, I believe it cannot.
But if there were 2 points x star and they got squashed together, then that you'd want to separate them out.
Yes. So in the case of one point compactifications, we cannot detect the direction of divergence for actual solutions.
Yeah, and also if you have blow-up profiles which oscillate to infinity, then in that case, the horizon, I mean, the point will also consist of periodic orbits. I mean, then there would be a lot in this point, right?
Yes.
But nevertheless, if you could, but I understand you can't, but if you could desingularize that, that would be an advantage because you don't have to search for the point where you converge to. Anyway, so it can't be desingularized. I believe that.
I have a question.
Yes.
Very nice talk.
Yeah, thank you so much.
So to make things harder for you, if you were going to use this technique to study blow up in PDEs, many things will be harder.
Yes. Actually, we have introduced this technique about 4 or couple of years ago, and I received the same question at that time when I gave a talk about this topic. But unfortunately, I don't have I haven't developed the machinery for the treatment in PDEs yet, because in typical PDEs, the Laplacian or some of the distributive operator is included for characterizing the solutions. But at infinity, such a dispersion effect completely disappears. Yeah, I have tried for detecting blow-up solutions for nonlinear heat equations, but in this case, the Laplacian the effect of Laplacian completely disappeared at infinity. So the question here would be reduced to the treatment of solutions at the infinity in the case of infinite dimensional problem. But anyway, no appropriate machineries are obtained yet for infinite dimensional problems.
Mhm.
So in principle, you could, of course, do the same projections. Of course, that is no longer a compactification because you're in infinite dimensional space. It's not compact. But nevertheless, you could go to this infinite dimensional sphere and then could map that to the boundary of the sphere. But maybe then details become complicated because tending to infinity does not mean that that tends to. It depends on the norm which you consider is a Sobolev norm or so. That will be complicated.
Exactly.
I have also another question concerning the. So I wonder, what is there some kind of characterization of asymptotically, asymptotically quasi-homogeneous vector fields? So to say, it seems to me that at least there is a necessary condition for these vector fields. There must be some kind of polynomials. Is that right? So except maybe you can replace the integer exponents which you have in polynomials by non-integer polynomials, but you cannot use transcendental functions or some things like that. Is that right?
So the machinery introduced here can be extended in appropriate way, and I have tried extension of the present treatment to the exponential nonlinearity shown here. So in this case, we have considered the finite difference approximation of this PD. So actually we have considered ODEs with exponential nonlinearity. But in this case, the case homogeneity cannot be obtained. But some kinds of exponential homogeneity around the infinity is still obtained. So using such a homogeneity, we could derive the treatment of dynamics at infinity in the similar way to the present argument.
So that means that this assumption of quasi homogeneity is not really needed. So you can also extend it to examples where you don't have that. Do I understand this correctly?
Not necessarily. Ultimately, not necessarily, I think. Yeah. So the asymptotic case homogeneity is just one class for systematically characterizing blow-up behavior. I think, and I still believe that there are more generalized classes to systematically treat the blow-up behavior based on the present arguments.
And if you want to characterize these quasi-homogeneous mappings, then so
Yes.
is this a big set within the set of all polynomials, or is that just a small set in the set of all polynomials? So it's a bit difficult for me to understand. So on this glance here, how large this class of quasi-linear or asymptotically quasi-linear mappings is.
I'm not sure exactly, but I think all polynomial vector fields are included in the present class because the k-psi asymptotic the k-psi homogeneous part, namely the leading part, can be characterized by Newton diagrams, well applied in algebraic geometry. But unfortunately, I don't see obtain the general extraction of the k-psi homogeneity, but the arguments based on Newton diagram in algebraic geometry can show that all polynomial vector fields are included in asymptotically k-psi homogeneous vector fields.
Okay, yeah, that's a good answer.
This is my current opinion. Yeah, thank you so much.
So basically, so the Lorentz equations are AQH.
I think so. For appropriate choice of case, the type and the order. Yeah.
And so maybe that would, because to answer also the question of, to try to answer the question of Michael. So say if I have a non-polynomial vector field with some exponentials, with some sines and cosines, but then I turn it into a polynomial vector field, and the new resulting higher dimensional polynomial vector field would be, in following your argument based on Newton diagrams, it would be asymptotically quasi-homogeneous. And I wonder if by going back to the original non-polynomial vector field, you could also draw conclusions about probably about the blow-ups. So it looks like your setup could be very general.
Yeah, I believe so. Yeah, but not fully general. Yeah, and because we have to care about this kind of exponential nonlinearity or logarithmic nonlinearity in general. Yeah, but at least polynomial nonlinearity can be covered in my arguments. Yeah.
Yes, but my point is that if you start with say if you have an ODE with an exponential term, and you define a new variable to be, I don't know, v equals e to the u. Now v prime equals v, and then you can make it you can build a polynomial vector field out of the non-polynomial vector field. And perhaps by studying the dynamics of blow-ups of this new polynomial vector field would allow you to understand the blow-up of the original non-polynomial vector field. So in that case, perhaps you could kind of use that approach of yours for, to characterize blow-up solutions of vector fields without polynomial nonlinearities.
In this setting, my answer is yes. So we can characterize the blow-up behavior for transformed polynomial like vector fields. Then the remaining part is the inverse transformation to the original setting. So that's all in my opinion. Yeah.
But could it happen that in this inverse transform, then, so to say, a blow up which you found in the transformed problem is no longer a blow up in the original problem? So that's, so to say, the blow up is a consequence of the transformation and not of the not inherent in the original problem.
Yes. I missed this point. Sorry. Yeah, this is very good points. Yeah. So the final result in the original vector field depends on the choice of transformation and namely the transformation of original variables or time scales or compactifications and so on. So the composite effector of transformations can determine the final results. So sorry, Jean-Philippe, but it depends on problems.
I think it depends on problems, but I think for exponentials, cosines, and sines, I think things should be fine. I think it's more when you have, say, rational functions where you can where you have singularities. But we could talk about this, but I would be interested because that's a very good question. I had the same question at Michael, about how generic are these asymptotic quasi-homogeneous vector field, because it's a very appealing approach. But if it was clear that it's broadly applicable, and that's great.
And this terminology, I miss mentioning this point, the potential of the present arguments. So the present approach mentioned here can be also detected the finite time extinction or quenching behavior. Quenching here means that the solution itself going to 0 at the final time, but the differential blows up. Or oscillatory blow up behavior can be detected, but such a behavior is a result of composite effect of transformations among the different variables and time scales. But the current approach is can be applied to quite general classes of vector fields. So it is worth thinking of the problems you mentioned. To detect the final behavior of solutions.
Okay. All right. Are there any more questions or comments? So I think I'm not going to push for more questions. It's already 24 past midnight in Fukuoka. So I think I think Kaname deserves a break. So I mean, I would like to thank you on behalf of all the participants. I would like to thank you very much, Kaname. If you look in the chat, there are many people who said thank you for the fantastic talk, Kaname. That's from Jay. Thanks for the great talk from Elena. The people had to leave. Thanks for a very interesting talk from Andrew Burbanks. Anyway, you can look in the chat. So you got many signs of appreciation there. So thanks a lot once more. It was a good talk, very good, very interesting, very sparking lots of interest. So I guess this is the end of today's seminar, and we will see you all next week. For Jonathan, I guess Jonathan, you're the speaker next week. You'll talk to us about very famous.
Thank you so much.
Okay. Bye-bye. Thank you very much, Kaname. See you all.
Thank you so much, everyone.